by Professor Subhash Kak. I have pleasure introducing him. Professor Kak is Professor and Head Department of Computer Science at Oklahoma State University, Stillwater, USA. He obtained his bachelor's degree in electrical engineering with distinction from Jammu and Kashmir University in 1967 and the PhD in electrical engineering from IIT Delhi in 1970 on the topic Studies in Signal Theory. He served the Department of Electrical and Computer Engineering, Louisiana State University in various capacities from 1983 to 2007. He moved to the Oklahoma State University, Stillwater in 2007 as head of the department. I should mention that Professor Kak has also served IIT Delhi from 1971 to 79, besides having various visiting fellowships at several renowned universities and research laboratories. He's on the editorial board of several journals and has won numerous awards and honors, including the Distinguished Alumni Award of IIT Delhi in 2002. I should mention that Professor Kak has also distinguished himself from conventional computer scientists by studying extensively and publishing in the area of theology, where he has several books authored by himself also on the subject. I invite Professor Kak to deliver his talk.
Thank you. My talk is going to be an out-of-the-box survey of where we are as far as quantum computing is concerned. In fact, I was asked to give a similar talk last year in November in Halifax, Canada, where CFAR, which is an organization in Canada, which decides on which particular fields of research should be funded in the future, had put together a symposium where they had invited people representing different perspectives on where the subject was going. And so I put this together, and as you'll see, what I'm going to do is not just speak of the mathematical framework, which is of course extremely attractive, which is what has led a lot of people to analyze it, and which gives us the attractive promise with the potential that you can do certain things in a manner which is not possible in classical computation. For example, Fourier transformation in log n square rather than n log n, although this Fourier coefficients are not actually accessible, but still one can see if the great revolution in signal processing of the last 30 years was a consequence of doing discrete Fourier transform, not in n square but n log n, by making use of fast Fourier transform, then going from n log n to log n square using quantum processing represents another leap. Now, we are already aware that two specific algorithms that have attracted people to look into this are the fact that database search can be done in square root of n rather than approximately n steps, which is the best we can do using classical algorithms, and factorization in log n rather than square root of n, for which the motivating problem was the problem of cryptography, since RSA is one of the standard methods which is used for key distribution in current technology. So if you could factorize in log n, that would make the RSA algorithm susceptible to be broken, and therefore this would tell us as to which other directions we need to go to develop techniques of the future. All right, now of course we all know what quantum primitives are. We have superposition of component states and collapse upon interaction, which is different from what we can do in classical systems. And a qubit is represented as a unit vector, and a quantum computer just rotates a state. And this, of course, itself tells us that quantum computing would be appropriate for problems where the representation of the problem can be modeled in such a fashion so that the solution can be viewed as a rotation, as an appropriate rotation. Now, of course, it's known that almost any problem can be mapped into a rotation problem, which is reversible. But in classical computation, that requires a lot of overhead, because in order for a transformation to be invertible, not only do you need to carry forward the intermediate steps, but also the input state. And what that means is that in most situations, for problems where rotation is a natural representation, not all computational problems would be properly modeled in that fashion. Now, the fact that factorization problem is so modeled, which is how the Shor algorithm came to be discovered, is because of the Fermat-Little theorem, where we know that with respect to a prime, since the numbers less than the prime form a multiplicative group, as you combine these numbers, you come back, you make a complete rotation. All right, now a quantum register is just like a classical register, excepting that each cell has a qubit rather than a simple bit, where therefore you can simultaneously represent 2 to the power n states, in contrast to a classical situation we can represent only one state. And these are, of course, some of the basic quantum gates. And we know about the control NOT gate, which is a generalization of the XOR gate. Now, what we need to do is to look at what has become possible for us to do in order to determine, what the prospects are, where are we going, what does the roadmap tell us. Now, we heard Dr. Vishal Sani tell us that in the next 5 or 10 years, we expect to be able to come up with systems which can process 20 qubits, or perhaps in some more time, 50 qubits. So to see how realistic that might be, let's look at the whole question of how do we form judgments about how much we have achieved in terms of implementation, because these judgments would then let us form a reasonable idea of what might be possible to be done in the near future. So let's look at the whole question of testing of a CNOT gate. Now, the results that we have is that, okay, people have implemented CNOT gate, and there are certain properties that people have published, but should we need to test a CNOT gate only for the specific inputs related to the qubits being 0 and 1 at the 2 input points or 2 input terminals? And it appears to me that a CNOT gate should not be tested only for these 2 values of the input, or 4, the 4 different combinations, 0, 0, 0, 1, 1, 0, and 1, 1, but also where you have the amplitudes A, B, C, and D as well. In other words, we need to test it for the inputs being A00 plus A01 plus A10 plus, sorry, B01, C10 plus D11, because it's quite possible that a CNOT gate that has been implemented is working appropriately for the values where A, B, C, and D are zeros or ones, while it doesn't work so well for other continuous values of the probability amplitudes. And this creates a kind of a problem. And what's the problem? That in order to test it for the general probability amplitudes A, B, C, D, you need to generate 2-qubit states with arbitrary ABCDs. And in order to do so, you need to have a CNOT gate or a functioning 2-qubit gate which is already available. So it creates a kind of a vicious circle. Because how do you test a qubit? How do you test a gate, a 2-state gate, a CNOT gate, unless you don't already have a perfectly functioning 2-qubit gate? Okay? So I believe that's a problem. Now, of course, one could respond by saying that since if we have a qubit gate, a CNOT gate, which is a perfect quantum system, then testing any two would be fine, because then by extension we would know that it would work for all possible combinations. But that remains to be established, since in any implementation there are going to be correlations or entanglements between the controllers which are operating upon the CNOT implementation, the CNOT gate implementation for those specific values. Therefore, it appears to me that this is something that, that creates a complication. Now, this is of course a simpler test that you go from 0, 0 to 0 plus 1 and 0, then you do your CNOT and you get a entangled state. And while what people have done is, for example, looked at spin in this particular fashion. For example, in the well-known measured CNOT logic truth table by Wineland's group, which is published in Physical Review Letters. And here the CNOT gate is implemented by means of this beryllium molecule in ground and excited states, which represent N0 and N2. And as you can see, the input state was prepared with over 96% accuracy, and this is the kind of a truth table that you obtain. But the probabilities do not add up to unity, because the data represents the sum of 4 different experiments, and there are imperfections in the state and analysis pulses, as well as limited gate fidelity. So there are all kinds of problems which remain to be overcome, because if this represents the best implementation that we have at this point, what this tells us is that the most fundamental building block that we need has a performance which has substantial error present in it. And therefore, one would need for further advances, also in terms of the choice of the technology, which is something that Dr. Vishal Sahni spoke about. And we don't, at this particular point, have consensus on what is going to be the most realistic way of doing things, or the most attractive way of doing things for implementations where we are dealing with 5 or 10 or 20 qubits at the same time. Now, there are other problems such as decoherence, which we all know about, which impose a time window which is extremely small, and therefore the entire problem needs to be solved within this extremely small time window. Now, the other side to this is the claim that maybe this could be effectively overcome by means of error correction. And if you can stabilize the state as it gets distorted because of random errors by performing error correction code, therefore effectively we would be able to overcome this decoherence limitation. And therefore the whole question of error correction becomes central, as people have recognized for a long time. What is the improvement, or what is the capacity that quantum error correction codes give to us, which would tell us that implementations of quantum computers, which mathematically do tell us that here we can do certain problems much more effectively in a manner which classical computing cannot do, and therefore which represents an entirely new frontier of computer science. So error correction therefore remains central, and the question of realization of gates is also extremely important. The two algorithms that we have, namely the Shor algorithm and the Grover algorithm, require a specific initialization of the register, and therefore the problem of how accurate that initialization is and what would the deviation from the initialization state, which is say the all zero state, what complications might this lead to as far as the evolution of the solution process is concerned, would be important. And there's also this whole question of certification. See, in classical computation, it's understood that whatever goes into the electrical circuit is what it is supposed to be. In other words, if you're using pulses of a certain kind, you can copy those pulses and check for yourself that indeed they are what they are supposed to be. Now, you can't do that in quantum computation. Why not? Because let's say there is a certification authority, or there is somebody, the supplier of the equipment, and he tells you that at this particular point in the circuit, you are going to be having entangled qubits, right? But how do we confirm that they are indeed entangled qubits? You can't check it, right? Or you may have a circuit where you're using entangled qubits, but neither can you check it, and nor do you know that these two qubits are not in turn entangled to another qubit, which is available to somebody else, who would then be able to sort of snoop on or able to reduce your state. So these are issues which are important, because all transactions or all computations need to be certified in some particular fashion. And here, that doesn't seem to be possible. It doesn't seem to be possible, for example, in the application that was described in the previous talk, namely teleportation, right? We have an unknown state which we are trying to teleport to a remote location, right? And for this, you need a pair of entangled qubits. One of them is with Alice, the other one is with Bob. But how do you know, or how does anybody know, that the two qubits that are with Alice and Bob are truly entangled in the manner that they are supposed to be? Now, if you had a single pair, you would have to test it, and you cannot make any conclusion based on any single pair. Okay? So this does lead to certain conceptual issues related to validating what is being done, even though what is being done is accurate. You know, you might test it out for several cases, but still not know whether a subsequent application or a subsequent performance of the computation would still be giving what you're supposed to get. All right, now I do want to speak very briefly about error control. In classical error correction, which is a part of all communication or of storage of computation, what happens is that a value x is received as the value y. So y is x plus n, where n is a random deviation from this value x. In classical communication, this x is represented as a pulse. And this x can be 0 or 1. If it's 1, it could be a positive pulse. If it's 0, it could be a negative pulse, right? So what is received is a distorted pulse, which can have in potential an infinity of values from minus infinity to plus infinity. Now, a very, very large proportion of these values are corrected by means of nonlinear processing. So you receive this pulse, what was the amplitude 1 could be 1.01, 1.5, could be 0.1, and all of that would be mapped to the value 1 because the threshold is 0. Anything above 0 at the point of sample is taken as 1, anything below 0 is taken as 0, right? So most of the errors are corrected through this nonlinear processing. Now, in addition to these errors, there are certain errors where what was transmitted as plus 1 is received as a value which is below 0, and therefore that gets represented as 0, right? Now, these are the large errors. Now, the probability of these large errors is small, and for communication applications, for example, you might take the probability of these large errors to be 10 to the power minus 6 or something of that order, let's say 1 in a million. But in reality, as far as the physical system is concerned, the error rate is quite large. That is the point I'm trying to stress. The error between, within the components and on the lines which connects components, or between the transmitting end and the receiving end, is considerable, but most of those errors are automatically corrected by means of nonlinear processing. Now, we cannot do that in quantum error correction, in quantum systems, because the whole quantum operation is a linear mapping, all right? And therefore, now, the quantum error correction models, which assume a logical 0, which could be a representation of many qubits, and a logical 1, which could be a representation of many other qubits, for which we have a theory which does tell us that if you have a certain error rate corresponding to bit flips or phase flips, you can make those error corrections small, for example, 10 to the power minus 6 or 10 to the power minus 5, where it's sort of being ignored that in reality the error rate for a classical system is much, much higher, accepting that as far as the end user is concerned, because of the capacity that is provided to us by nonlinear processing, we are able to come down from this much greater error rate to one which we are able to deal with using classical error correction codes. So to me, it does appear that this would remain a problem.
When you say that error correction assumes only bit and phase flip and not other changes, are you implying that any other error would not be corrected?
No, no, other errors would be corrected, but that would be possible only under certain assumptions that are made about the quantum error channel, that errors are independent, because if the errors are correlated and all the qubits, for example, taking an extreme example, suffer the same rotation, right? If they are correlated, then there's no way you can tell that apart from an angle, that a phase angle with respect to your basis vectors that was already not a part of that state.
The point I'm making is that's the same in classical error correction. I mean, the classical error correcting code would not be able to correct arbitrary errors. So that's the same in quantum.
No, no, it isn't. Because in a classical system, all small arbitrary errors are automatically corrected. All small, even if they are correlated. See, so long as, just look at this. Say we have a string of ones and zeros, which is going through. Since this string of ones and zeros is transmitted as pulses, even if all of these pulses suffer correlated noise, right, where the positive pulse, which represents a 1, becomes, say, 1.01, and a negative pulse, which represents a 0, becomes minus 0.9, right? They're all correlated in a particular direction. But that would not really be a problem, because so long as the noise is smaller than a certain threshold, all of that noise is automatically removed by clipping, by means of this nonlinear processing, which is available to you in classical processing. Now, the only errors, now of course there are certain other large errors that we can correct by means of introducing redundancy, right, to each block, assuming that we are doing block error correction coding. And that large error rate has to be smaller than a certain postulated rate for which a particular class of error correction codes have been designed.
Yeah, I guess I understand what you're saying now. But supposing you combine error correction, quantum error correction, with fault-tolerant computing. So there is they do define a threshold that if the errors are below a certain threshold, you can still get the job done. So, I mean, I understand that quantum error correction by itself, if there are these correlated errors, they may be very small, and then the threshold thing doesn't work. Whereas in 0, 1, if the error is below, let's say, 0.5, then you can still make a decision over there.
Right.
But if you combine it with fault tolerant, I suppose the same thing carries over.
Yeah, you're right. It can be done, but the overhead becomes progressively greater. And then the question is, and I think that's what tells us what is it that we need to focus on. If you're trying to, in our roadmap, if you are trying to develop quantum computational system with a certain number of bits, with a certain performance, maybe this is one of the issues that we need to focus on much more. What is the capacity with respect to our ability to correct errors as related to the overhead which would go with such error correction? And it appears that this overhead would become greater and greater. I'm not saying that that need necessarily be true, but I think the test here would be, well, are the error models that are a part of the mathematical analysis of such quantum error correction codes indeed realistic? Is that what we would encounter in an implementation scheme? And as we saw from the results that the Wineland group has on the performance of a CNOT gate, that that particular implementation itself has a tremendous amount of error, right? Now, if these errors that we are going to get are not only going to be coming from interaction with the environment, but also from within the gates, from the implementation that we have, and also the interaction between the control circuitry and the quantum computational system that we have.
I just want to point out it's not quite correct what you said. For arbitrary errors, as long as they're very close to the identity, just like in the classical case, by measuring syndromes, we can perfectly correct that.
Even if they are all totally correlated?
Yes, as long as it's very close to the identity. Again, it's just like the classical case.
Well, let's just imagine that we have a qubit, which we can view as this vector, right, on the unit circle, and let's say it suffers a rotation through a certain angle. And how do you know whether it was originally supposed to be at that particular orientation or the orientation that it has now, if you don't have anything to compare it with, right? So you need to have a reference. And you do have a reference in a digital system, because in a digital system, in a classical digital system, you only have zeros and one values. While in an analog system, you can have a reference if there is a certain value which you know has not suffered this rotation. If there's no value that you can guarantee, if the frame itself has changed, for example, then you will not be able to tell.
By the design of the error correcting code, though, this small logical rotation, in fact, has to be done by a unitary that's very far from the identity, right? So we're discussing very low noise rates. That's not something that happens by very low noise rates. You would need something very high for that.
Okay, we can sort of go on to this later. All right, now I also want to talk about a couple of other things. One is if one were to look at controlling a gate, you want Y to have a certain entropy associated with it. Entropy in the sense of variety. If you're looking at it as signals or values which can vary over a certain range. Now, that can be ensured only if the entropy of the controller C and the entropy of X is equal to the entropy of Y in any information system. Now, if because of noise within the gate, there is a lot of error that is coming in, that needs to be countered by the controller. And this leads to certain issues related to how much of such noise can actually be dealt with. Because if you have continuous change, we know that the entropy of a continuous variable can be infinity, right? And therefore, this brings up certain issues about the controllability of gates. Now I want to talk about another matter which is concerning the whole issue of entropy in a information theoretic setting. Now the von Neumann entropy, as we all know, is S rho, which is minus summation lambda I log lambda I. And for a mixed state, it corresponds to the expression here, which is similar to what we have in Shannon entropy as well. So as far as our intuition of entropy is concerned, it's perfectly reasonable for the von Neumann entropy to have this value. Now the only problem that we have here from information perspective is that for an entangled state, well, for a pure state, the von Neumann entropy is 0. Now, that is somewhat problematic for two reasons, as far as our intuition related to information is concerned. And the reason is that, first of all, in this specific example, an entangled state, this particular entangled state is a pure state, its information is 0, its von Neumann entropy is 0, but the two individual qubits are in a mixed state, and therefore they have finite von Neumann entropy, right? So here we have a state where the components have a finite value of information, but the system by itself has 0 information. Now this may not appear perfectly okay to some people, at least from a conceptual or intuition point of view. But from another perspective, which is the perspective where we assume here we have Alice in a room and Bob in another room. Alice is preparing an unknown quantum state and making a very large number of copies of this unknown state and sending them to Bob in the other room. Now, Bob can perform experiments on these very large number of copies of this state, and by means of these experiments, determine what this unknown state was, and therefore obtain information. All right. However, the von Neumann entropy associated with this pure state, which is being prepared by Alice, is 0. Okay. So here we have a situation where we can obtain information by experimentation, where Bob can obtain information, and therefore this is a framework in which information is being transmitted across from A to B, where the measure of entropy, that is a part of the whole mathematical framework with all its power and so on, does not seem to be adequate for our information purposes. Here we have a preparer of states A trying to communicate the ratio A over B, which is M, for example, to B, where A and B are real and the state is either pure or a mixture. If it's pure state, then what Bob has to estimate are the values A and B. And since there are many, many large number of copies of it, that is possible. And therefore, each measurement is giving Bob a certain amount of information. Or even if it's a mixture, once again, that is possible. So as a kind of an ad hoc measure, which would also associate with some information with a pure state, a couple of years ago, I proposed that maybe you could define an informational measure of entropy for the quantum situation as minus summation rho I log rho I, which would then which satisfies properties such as this. And the very last one is that that this informational entropy measure is greater than the von Neumann entropy. And that's because if the state has a pure component, that also carries some information. Here's an example where the proposed ad hoc measure gives us 0.868 bits, while the von Neumann entropy is 0.798 bits. So there seems to be a difference between these two values. Here is another example which says the same thing. this is an ensemble consists of pure and mixed components as follows, and that is what entropy we get. So I mentioned this as something that may be worthy of some analysis to see if this measure, the proposed measure, or maybe some other appropriate measure, which also helps us associate information with a pure state, would be something that from which some other intuition could be obtained. Because, you know, the intuition that we have is if there's something unknown, and then this unknown should have some information associated with it. Of course, if it is something known, then it has no information. That is the classical intuition that we have associated with information. Now, finally, I want to speak of a quantum cryptography protocol that I published a couple of years ago, which is different from the BB84 protocol that some of you may be interested in. And here the idea is that Alice and Bob exchange qubits between them over three-stage process on a three-stage protocol. And what each one of them does is to perform a transformation which is private to each one of them. So Alice takes X, which could be 0 or 1, the qubit 0 or 1, or some other superposition, and performs her transformation. Bob receives this qubit, performs his own transformation, and then so long as these two transformations are from a class which commute, Alice takes the complex conjugate of her transformation. And if they are rotations, so basically what is happening is Alice performs a rotation, Bob performs some other random rotation, Alice reverses her rotation, Bob reverses his rotation, and therefore this qubit X or information X has been transmitted from Alice to Bob. And this is something which is unbreakable, because the mapping that Alice and Bob perform can change from qubit to qubit. So if the problem was to share a key, and you need to do it for a certain number of qubits, they do it, and then this key could be used as a seed to generate a random sequence, which is what is done these days as well in cryptographic systems. Now, the intuition behind this three-stage protocol is an old story that all of us have heard when we were children. And the story is, how do you transport a diamond, or how does a person send a diamond in a box, a jewelry box, over a remote distance through an untrustworthy servant? Okay, so how do you do it? He takes this diamond, puts it in a box, applies his lock, and the servant takes it. Servant ordinarily could have broken this lock, taken the diamond, replaced that with a piece of plastic, put it in a nice box, put another lock on it, and taken it to the remote location, right? And that person would have never known whether the sender had sent this or the claimed diamond. But now what happens is that this box goes to the location Bob, and Bob puts his own lock on it, sends it back. Alice checks whether the lock that she had put on is tampered or not. And if it's not tampered, she removes it, the box goes back to Bob. Bob can check whether the lock that he had put has been tampered or not, and therefore the contents of the box are unaffected, and therefore this sort of ensures that there is total confidence that one can have in this whole process. So now, concluding remarks, I think while quantum computing as a paradigm has been wonderful in a variety of ways, as a mathematical framework, as providing directions for physicists and for people who work at the nano scale levels in doing things which were not possible to anticipate earlier on. I believe it also implies attention to certain issues which are not as serious in classical systems, such as the whole question of errors. I think assumes a much greater importance, and I think that is something that one might want to focus on in relation to whatever roadmap one might have on implementation of these systems. And the other insight or matter which may be of some relevance theoretically may be the whole question of quantum information where observers are involved. If observers are not involved, then the matter of von Neumann entropy, I think, is wonderful, because for physical systems, that is the natural measure of entropy that emerges out of the framework. But if observers are involved, then clearly, at least it appears to me, the von Neumann entropy does not capture all elements of the intuition of information, of what it is possible for A to communicate to B. And the question that arises then is whether this transactional nature of quantum information may be of relevance to other models or other paradigms that are used in physics. And if it is, then you know, there may be something interesting theoretically or mathematically also that would be able to come out of it. Here are some of the publications on these ideas that I have published. Now, let me also say that it's also possible to suggest that the circuit model of quantum computation may not be the only viable model of quantum computation. And this is something that theoreticians might wish to think about, because as many of you know, there are computer scientists who have argued that the protein folding problem is a NP-complete problem. You know, the protein folding problem is the problem of this one-dimensional amino acid chain for which the molecules must satisfy certain constraints, which, if left to itself, folds itself into a 3D structure. Now, it's been argued that if this chain had, let's say, 100 elements to it, being an NP-complete problem, a classical computer would take an inordinate amount of time, you know, thousands of years to solve it. But nature solves it in just a few seconds. And it's quite possible that what it really means is that, that nature is using quantum computation of some kind to solve this problem. And it's being solved because, if this statement is correct, that quantum computing has a power which is much greater than that of classical computation. But certainly nature does not solve it in the circuit model paradigm of the kind that constitutes quantum computation right now. So the question that one might ask is that, is there some other way that the whole quantum computation framework could be represented, which may also serve as a fruitful framework, as a fruitful paradigm? Certainly, the network model has been very fruitful. It has led to a lot of advances, both in our insights related to how gates can be combined, or you need certain universal gates, which, if taken together, can represent the general unitary transformation, which is the solution to the problem that we have at hand. But is it possible that this could also be done in some other way, which would continue to be a general quantum computational framework? So finally, I suppose one would say the whole framework is, of course, of the most absorbing interest on a variety of levels. Theoretical, which is the reason why so many physicists, computer scientists, and mathematicians are working on it, and challenges by way of implementation. And I trust that that's going to lead not only to the kind of advances that Dr. Vishal Sani outlined in the beginning, which is a part of the roadmap in India and internationally, but perhaps unexpected advantages that, or unexpected and surprising results that we don't even know what they are. Thank you.
We can take one or two questions.
Kind of a troubling feature that the entropy of a composite, von Neumann entropy of a composite system can be less than the von Neumann entropy of the subsystem, which in another way is saying that the quantum conditional entropy could be negative. But to me, von Neumann entropy derives its strength from, because it has an information theoretic meaning to it, and which comes from the Schumacher's noiseless coding theorem, or the quantum data compression. So an alternate measure, whichever is proposed, I mean, does it have a information theoretic meaning to it, and what is it? And then maybe we can say that maybe it doesn't have these issues that the entropy of a subsystem can be greater than the entropy of the whole.
Yeah, I think that all remains to be investigated. Yeah, so we don't know, and they are absolutely valid points to make. Yeah.
Actually, my understanding, the bottom of the entropy of the state is zero because it's not actually entangled with anything else. And therefore, its von Neumann entropy is zero. Now, if you take a maximally entangled pair, as you did, the information content is precisely in the entanglement between these two, which is actually maximum, and that's why you can do super dense coding and so on. So I don't really see any conceptual problem in this, A. And B, the kind of measure which you actually propose is strongly basis dependent, I guess. So such a thing will have some problems, right? I mean, because whatever is sort of physical quantities that come out of quantum mechanics, one would expect it to be basis independent in some way.
True. I certainly agree with that. From a physics point of view, they should be independent of the observer, right? So they should be invariant with respect to measurement basis, for example, which is why the von Neumann entropy is the appropriate one from that perspective. And that's the reason why I asked the question from an observational point of view. Is it possible? And I'm not even suggesting that that the answer has got to be in the affirmative. But is it possible that since our intuition related to an unknown pure state prepared by Alice, and here we are receiving copies of this unknown state, and we can obtain real information from this pure unknown state, right? Which doesn't seem to be captured by the von Neumann measure. So is it possible that for such information transactions, is it possible that something else is needed? Certainly not for physics. It's quite possible that what you're saying is the last word on that. And all that I'm saying is that this may be worthy of some further examination. And it's also quite conceivable that upon such further examination, you might say, well, really, we can't do anything. But be that as it may, it is certainly true that you can obtain information from an unknown pure state, you know, if you have many copies of it. And, you know, if one were to step back and talk very speculatively, there is a paradox which is called the information paradox. I think Penrose mentions it in his book, Shadows of the Mind, which is the paradox that early universe was fairly uniform, and therefore its entropy was small, right? And now, after all these billions of years, the entropy is much larger. So how come entropy has increased, right? And one answer, in an extremely speculative sense, would be that if there were observers, or if observers or observation is a process which is a part of this evolution a priori, because observation reduces a pure state and therefore increases entropy, then one could see how entropy would increase over the evolution. Because if there were no observers, then this entropy should remain the same, assuming that you know, you have a system, it's a pure state, the initial state of the universe is pure, it evolves, so it should remain the same. And therefore, it could lead to, at least on foundational or speculative basis, certain opportunity, if you will, of posing problems in a new fashion, which may be useful in some sense. I don't know. Yes.
So you talked about the CNOT gate, the experimental realization of the CNOT gate. And you said that so of course if it works on the logical basis, it works properly. Right? So the 0, 0, 0, 1, etc. But I mean, how does it guarantee that it will work similarly on the other?
Right.
Okay. So basically you are questioning at the linearity of the gates, right?
Right.
So this problem will remain in the classical gates also.
Precisely. Okay, you put it very well. If you are absolute, if you guarantee it's a perfectly linear system, then you have to check it only for a certain number of values, and you will be sure that this works. But we don't know whether the actual physical implementation of this gate is purely linear. Now, for the classical case, it doesn't really matter, because in the classical computation paradigm or classical communication paradigm, non-linearity is what we are taking advantage of. And non-linearity can deal with whatever non-linearity is a part of the system. Because you need for the system to work perfectly only for those two values. All other values, it's not working perfectly, that can be gotten rid of by means of clipping or by nonlinear operation, which is something that you cannot do in a quantum system. And therefore, I think this leads to a problem which may not have received as much of focus as it ought to. this whole circularity. You know, you need to, first of all, also to generate all such values, and you know, in engineering, looking at it from an engineering perspective, testing is one of the most important things in an engineering system. And how do we ensure that whatever you have constructed is indeed working the way it's supposed to be working? And so that would need to be dealt with.
Last question, please. Okay.
So if you assume that quantum mechanics describes your system,
Right.
in that case, it's certainly not necessary to check
Right.
every input.
Right.
On the other hand, if you don't believe quantum mechanics describes your system,
Right.
I would say there are much more fundamental issues than,
Right.
than whether a quantum computer will work. I mean, of course, a quantum computer doesn't work if you don't believe quantum mechanics.
Yeah, the problem is, you're absolutely right. If it's a system which is completely described by quantum mechanics, then you don't have to. But the whole problem is that the way these systems are implemented, what the experimenters have shown that, well, you are getting, let's say, 98% fidelity with respect to this particular transformation without checking whether for other probability amplitudes, the kind of entanglements between the controlling circuitry and this equipment create a system which is not completely quantum mechanical over all possible values.
But of course, they don't only check the 0, 1, 1, 0, 0, 0, and 1, 1, right? That you see these 16 by 16 plots, so they can confirm the existence of coherence. And, like, they can do much better than I think what you're suggesting.
They do, but as I was telling you just a couple of days ago, we had the leading optics guy from University of Wisconsin, whose name I forget now. He had come to our university to give a talk on generation of entanglement in his group at Wisconsin. And the fidelity measure for it to represent total entanglement is 1.0, and no entanglement is 0.50, and the result that he had was 0.53. And he wasn't sure that this departure from 0.50 to 0.53 was not a consequence of measurement artifacts. So there are all kinds of challenges which people still seem to encounter in their actual experiments.